2 will be given by Gokul Ravi. Gokul Ravi is a 2020 NSF CI Fellows postdoctoral scholar at the University of Chicago, who is being mentored by Fred Chong. His research targets quantum computing architectures and systems, primarily centering on themes at the intersection of quantum and classical computing. He received his PhD in computer architecture from UW-Madison in 2020 and was advised by Professor Mikko Lipasti. He will first be telling us about his work on developing a better than worst case decoding algorithm for quantum error correction. And then he will follow by telling us about his approach to navigating the dynamic noise landscape for variational quantum algorithms. And so without further ado, I will go ahead and leave the floor to him. And please feel free to move up if you're comfortable doing so, you know.
Yeah, thank you, Sarah. Yep. I hope I'm audible. Yeah, I think I should be. Okay. Yeah, thank you. So hello, everyone. I'm Gokul. I'm a postdoc at the University of Chicago. So first, I'm going to be talking about CLIC, which is this better than worst case approach to decoding for quantum error correction. So a better than worst case approach is something which is common in like architectures and systems where you're sort of separating the common case easy tasks from the rare hard task and handling the common case tasks in a low cost manner, and only the rare hard task can be handled in a more thoroughly at higher cost. And this is very useful in building like efficient solution to these kind of systems where you can separate these tasks into these two groups. And so in this work, we take this approach of better than worst case to decoding for quantum error correction, and we propose this kind of a novel decoding scheme which combines these two schools of decoding to achieve significant improvements over both those schools of decoding in different scalability metrics. And this work is a collaborative effort between UChicago, University of Southern California, and IBM. So I'll start with the background on quantum error correction. So qubits in general, both what we have today and in the future, will have errors occurring every once in every hundreds or many thousands of operations. But a lot of critical quantum applications require error rates which are much lower, maybe once every billions or trillions of operations. So there's clearly a gap between this, which we need to address. And this is where quantum error correction comes in. So quantum error correction is the idea where multiple physical qubits are brought together and encoded together to form one logical qubit. And the idea is that only a few of these qubits might have errors. And so we can use some error correction schemes, which is done through some classical processing to identify these errors and correct them so that we can achieve those very low logical error rates. Now, the challenge is that it's tough to identify these physical qubits which have errors. And this is because observing these qubits requires you to measure these qubits, and measuring them means that they will lose their quantum state, and you don't want that because the quantum execution is still ongoing. However, there are many theoretical approaches to overcome this, but they all result in the error correction decoding algorithm to be a pretty complex graph algorithm. And so that's a pretty significant bottleneck, and which is one aspect of which we are going to address in this work. So the scope for this work is cryogenic quantum systems, which is common in like superconducting qubits, which are like used by IBM, Google, and they are the most popular modality at the moment. And so this is an example of a cryogenic quantum system. You have these qubits which are located at this 20 millikelvin domain. Then you have some control logic, which is present at 4 Kelvin, and other classical processing, which might happen at 300 Kelvin, which is room temperature. Now, I'm going to talk about an example where we have 5 logical qubits, and each of these logical qubits, as I mentioned earlier, is a grouping of some number of physical qubits. And each of these logical qubits are what form this circuit, like the example I have shown at the bottom. Now, what happens is that every instant of time, new errors are being produced by these logical qubits. And the traditional decoding approach is that all these errors will flow out of the dilution refrigerator, and we have these complex decoders running these graph algorithms targeting each of these logical qubits, right? And the idea is that because all of these errors have to be decoded pretty quickly, and because if you don't correct them quickly, then they're going to produce new errors, and you will not be correcting for the errors which are being produced at the moment. So these errors have to be corrected quickly. And if we want to make this useful for practically sized algorithms, the bandwidth you will need at the interface of the refrigerator and the outside world would be running into many terabits per second, which cannot be supported by your traditional metal interconnects. So this is a significant bandwidth scalability problem. So there have been some other approaches which have moved this entire decoding scheme into the cryogenic domain. This, of course, alleviates the bandwidth bottleneck, because the bandwidth which can be supported by these superconducting wires between the 20 millikelvin and 4 Kelvin domain can support a significantly higher bandwidth. But the issue is that there's a pretty significant power and thermal limitations in this cryogenic domain, which means that we cannot have too many of these complex decoders within this domain, and therefore it's also a scalability bottleneck. So what I've told you so far is that, so there are these two common approaches to decoding. One is this outside fridge bandwidth constraint approach, and the other one is this inside fridge resource constraint approach. Now, though these approaches are fundamentally different, the commonality between them is that all the errors which are flowing from your qubits are being handled in the same way by this complex decoder, right? And it is this one size fits all approach that we are breaking in our work by using this better than worst case approach. So what we have identified is that these errors which are flowing out of these qubits can be separated into two groups, these trivial to decode errors and complex to decode errors. And the good part is that most errors are trivial to decode, and the separation between the trivial and complex can also be done fairly easily. And the high level idea is that within your physical qubits, which are forming a single logical qubit, if these errors are all isolated in space, then the decoding can be done easily, and these are the common errors as well. On the other hand, if these errors form a chain, then these are the ones which are hard to decode, and they are also more rare. So I'm not going to talk about why these are rare, because that just stems from probability, and I'm happy to talk more about it offline, but I'm going to discuss a little bit about why these chains are harder to decode while the isolated ones are easy to decode. But once this separation is made between trivial and complex, then all these trivial errors can be handled by this click decoder, which we designed, which is a very lightweight decoder because it has to handle only these very trivial cases. And this can be situated in this cryogenic domain. So going back to the system level view, so what this means is that this click decoder sits in this cryogenic domain, one for each logical qubit. It's very low power, and low thermal requirements, so it can, you can put many of them within the refrigerator, and it's only these few of these errors which cannot be handled by click, which has to go outside the fridge, and those will be handled by your state-of-the-art complex decoder. So both your bandwidth as well as your thermal power bottlenecks are reasonably alleviated, and this is significantly contributing to the scalability of these cryogenic quantum systems. Okay, so now I'm going to talk a little bit more about this work in the context of surface codes. So surface codes are a type of quantum error correction codes, which are especially suited in the near and intermediate term of quantum computing because they are suitable for higher error rates and they require less connectivity and so on. Happy to discuss that more later. The idea is that each logical qubit is encoded in d squared data qubits, where d is something called the code distance. The higher the code distance, the more robust the system is to errors. So you can see these 9 data qubits over here. So this is a code distance of 3. Now we have these, what we call parity qubits, which are surrounding these data qubits. And the reason why we need this, because as I mentioned earlier, we can't directly identify errors on these data qubits, and we are using these other supporting qubits to help identify errors. So for example, if we have an error in this data qubit D in the middle, the effect of this error is seen on those diagonally adjacent X qubits, and they could also be this diagonally adjacent Z qubits if it was a different type of error. Now, what a decoder would do is that it looks at these yellow things, which we call syndromes, and identifies that therefore the error has to have originated from this red data qubit, which is in the middle. And then that error can be corrected, and so the computation can continue error-free. And so, okay, so with this, I'm going to now dive a little bit deeper into why error chains are hard to decode and isolated errors are easy to decode, because that is the main crux of the click decoder. So assume you have this kind of a lattice where you have 2 syndromes which are fairly spread apart, the yellow 1 and 2. Now let's say you try to decode this. And if you did try it, you might have identified that a possible error chain, the most likely error chain which caused these errors are this red sequence of A, B, C, D, which I show over here. Now, the way you might have actually found this out is by trying out different error chains. And you might have selected this red error chain because it's the least, the sequence length which could have caused this error, and therefore it is the most likely, right? This is a maximum likelihood method. Now, the way this is actually done in a robust manner is by using these kind of graph algorithms, which I mentioned at the beginning. And that's why doing this requires your complex decoder when these error syndromes are spread far apart. Now, imagine this other scenario where you have these locally paired error syndromes. This 1 and 2 you can see over here, and this 3 and 4 you see here. Now, if you try to decode this, you might have identified that the most likely errors are this red A over here and this red B over here. Now, if you did do this decoding, you could have done this without looking at the rest of the lattice. That is, you could have identified that A is a likely error by just looking at the syndromes 1 and 2, and similarly that B is an error by just looking at 3 and 4. Now, the key aspect here is that you can identify this without looking at the rest of the lattice, and this is exactly how the click decoder works. So each unit of click looks only at a localized portion of the lattice, and this is why it is extremely lightweight. So I should mention that there are some additional requirements to ensure that this works properly. You have to ensure that these errors are in fact a coupled pair, and also that these errors are not caused by some other measurement errors and so on. But even doing all this is fairly simple because of how isolated, the fact that you can actually do this decoding without looking at the entire lattice. Now, after doing that, so I'm going to go into some of these results. So in terms of, so first I'm going to discuss the bandwidth reduction in terms of the complex errors which have to flow outside the dilution refrigerator. So you can see here that over different scenarios of physical error rates, more than 90 to nearly 100% of all the errors can be handled by this, by the click decoder. And you can see that as the qubit error rate decreases in this graph, as you go from left to right, the fraction of the errors which can be decoded by click increases. And the reason for this is that as error rates decrease, the probability of having these chains of errors which are tough to decode decreases even more. And in comparison to some recent work also focused on bandwidth reduction, this work achieves many orders of magnitude improvements because the prior work uses like an error compression scheme, which can be good sometimes, but not in other scenarios. But click decoder is always useful as long as the errors are isolated. So we also made some comparison to other work which does this entirely cryogenic decoding, and we identified that because the click decoder has such a lightweight design within the refrigerator, it can support many more physical qubits, like 2.5 million physical qubits for a power budget of 1 watt, which can lead to many thousands of logical qubits, and is 25 to 80x more power efficient than the most similar prior work. And this is at lower code distance, but when you go to a higher code distance, the benefits will be even more because of linear scaling for this click decoder. With that, I'll summarize the work. So QEC, that is quantum error correction decoding, suffers severe bottlenecks in terms of bandwidth, power, thermal, and so on. A better than worst case approach is where you separate these common errors from the hard errors is very useful to do this kind of decoding. And to do this, we build this click decoder, which is this cryogenic decoder, and it achieves many orders of magnitude improvements over the state of the art. Yeah, thank you, and I'm happy to take questions.